Kalikamuya, Daniel Jacobs, Alex Hibbs, and Ali Reno.
MRI safety and instructional video.
Hi, my name is Dan Jacobs, and I work with Swag Technology to produce this instructional video. In this video, we will discuss various aspects of an MRI machine. First, we will talk about what an MRI is and an overview on how the process works and exactly on how an MRI is conducted. Second, we will take a look at the different parts of an MRI machine. Then we will talk about the physics behind the MRI. Lastly, we will discuss the safety guidelines that accompany MRI scans. Let's get started. Welcome. In this video, we will be discussing how an MRI machine works and the physics behind it. To begin, let's look at the parts of an MRI machine. Let's go. First, let's look at the primary magnet. It's a permanent magnet like the kind you would use on a refrigerator door. That's powerful enough to use in an MRI machine, but it would be too costly to produce and too cumbersome to store. Another way to make a magnet is to coil electrical wire and run current through the wire. This creates a magnetic field within the center of the coil. In order to create a strong enough magnetic field to perform an MRI, the coils of wire must have no resistance. Therefore, they're bathed in a liquid helium at a temperature 450 degrees Fahrenheit below zero. This allows the coils to develop a magnetic field that's more than 20,000 times stronger than the Earth's magnetic field.
Oh my gosh, that's huge.
Gee willikers! In the next section, we will be discussing the MRI, or the magnetic resonance imaging. Let's take a look.
The primary magnet is a permanent magnet in an MRI machine. The magnetic fields projected by the primary magnets are used to align the hydrogen protons in the body. Gradient coils allow the MRI machine to focus on specific parts of the body. These gradient coils allow the magnetic field to be altered very precisely. The coil uses the Lamore frequency to cause a transition that allows all of the protons to spin in the same direction. Radio frequency waves are absorbed by the protons and emitted as a signal. The radio frequency coils picks up this signal and transmits it to the computer. The computer processes this data and produces an image. In the next segment of our presentation, we will be discussing the physics behind an MRI. Then later, we will discuss how each segment is important to an MRI. First, we will discuss the forces on a charge, the Lamore precession, Ampere's law, solenoids, induction, and magnetic torque. Now we will discuss the forces on a charge. This can easily be explained by using the right-hand rule. According to this rule, extend the thumb, forefinger, and the middle finger of the right hand in such a way that all three are mutually perpendicular to each other. If the forefinger points in the direction of the magnetic field and the middle finger in the direction of the current, then the thumb points in the direction of the force exerted by the conductor. An equation to show this is F equals QVB, where F is the magnetic force, Q is the charge, V is the velocity, and B is the magnetic field. As we discussed before, nuclei have an intrinsic quantum property called spin. When a magnetic field is imposed on the nucleus of an atom, this nuclear spin will orient itself according to the field.
The Lamore precession frequency is the rate of precession of a spin packet under the influence of magnetic field. The frequency for an RF signal which causes a change in nuclear spin energy level is given in the Lamore equation. This is the Lamore equation, where omega is the angular frequency of a precession of protons in the external magnetic field. V is a proportional constant, and B is the strength of the external magnetic field. V equals 2.6 times 10 to the 8th radians. Next, we will discuss Ampere's law. Ampere's law enables engineers to calculate the magnetic field around a loop, which is useful in studying the magnetic field produced by an MRI magnet. In addition to calculating the magnetic field, engineers use Ampere's law to determine the correct amount of current and voltage that is necessary to create a functioning circuit board and perform the necessary task. Magnetic fields are created by the spin and movement of electrons. Therefore, in a current wire anywhere creates a surrounding magnet field in a given area. The strength of the B field is directly proportional to the current.
Solenoid is a coil of wire with a uniform current. It creates a uniform magnetic field due to Ampere's law. Each loop or coil has its own magnetic field, the B field. All B fields combine to produce a larger field. By wrapping the wire, the magnetic field increases. A coil is a large inductor with a considerable dimension and defined wavelength, commonly used in configurations for MRIs.
The strength of a magnetic field created by a solenoid can be shown using this equation. B equals mu Ni, where B is the magnetic field, mu is the constant, N is the number of coils, and I is the current.
Electromagnetic induction is the production of voltage across a conductor moving through a magnetic field. Current is affected by magnetic fields, but B fields also induce currents. Faraday's law of induction indicates that the induced electromotive force, EMF, and the change in flux have opposite signs, and it also gives the direction of the induced EMF and current resulting from electromagnetic induction. Voltage is equal to negative N, or the number of turns, multiplied by change in magnetic flux, all over time. This equation shows how an induced electromagnetic force could cause these particles to flow. It shows how we are able to produce an electric current within the body. When a loop of wire is placed in a magnetic field, the magnetic force can produce a torque. Torque will tend to align along the magnetic field's lines. The torque increases with field strength, while the attraction increases with the gradient of the magnetic field.
As you can see, the MRI gives a very clear and precise picture of the different parts of the body, using different shades of gray to determine tissues and different body structures. Let's put it all together. But first, we need to learn what induction is. Induction. It's the energy of voltage across a conductor moving through an electromagnetic field. It underlies the operation of generators, all electric motors, transformers, induction motors, and solenoids, and most other electrical machines. So, are there any questions?
What are the physics behind an MRI?
What are the precautions to having an MRI?
And what does it feel like?
Recent studies show that all potential hazards have not been established regarding pregnancy. Therefore, an MRI is generally not performed on a woman in her first trimester of pregnancy. There is no strong evidence that concludes an MRI is dangerous during pregnancy. Though caution should be taken regarding pregnant women because an MRI spins the hydrogen atoms in the body. This, in addition to radiation, should be potentially dangerous for a fetus. Tattoos are also dangerous in an MRI. About 20 years ago, tattoo ink was not regulated as closely as it is today. Some tattoo ink contains small fragments of metal. Patients with this type of ink reported a slight discomfort to severe pain during an MRI. The magnetic field pulls at these metal fragments and causes a burning sensation. In addition to the physical effects, tattoos with metal fragments can alter the image. Nowadays, ink is not made with metal fragments. Guidelines say that an MRI machine shouldn't raise our temperature more than 1 degree Celsius. Think about it. With a fever, your body temperature is already higher than normal. An MRI potentially raises your body temperature, and with a fever, even a slight increase could be harmful to the health of patients.
Next, we will be discussing the coils of an MRI machine. Sorry, class, you can't read this going. What are you doing here? You're not supposed to be out in public. Teaching a class?
Yes.
Teaching my class? Yeah. Go home. Sorry for the interruption, but let's get back to the lesson. When a patient enters an MRI machine, the nuclei of their hydrogen atoms spin one of two directions. The RF coils emit a radio frequency that will precess or align the spin of the atoms. This frequency is very specific and is called the Lamour frequency. As the molecules transition from a high energy to a low energy state, the exchange of energy is called resonance, hence magnetic resonance imaging. This concludes SwagTech's Grand MRI Challenge video. For more information, visit our website at http://www.pvworks.com/w/page/swag-technology-hp2. Enjoy the rest of your day. I don't know. I should have said that.